Hi viewers, good evening all of you. After a long gap, we are meeting once again, and I have slightly decided to take a detour, and we will be shifting from electricity and magnetism. Of course, we'll be continuing with electricity and magnetism also. We are going to start a new series of videos in the area of quantum mechanics or quantum physics. So let us get started. So, quantum physics is one of the most fascinating subjects that you can think of in all of physics. So, what exactly it is? What are its implications? Let us see. So, how do you define quantum mechanics? So, let's get into the very basic definition of quantum mechanics. It is a framework for doing physics. Quantum mechanics is essentially a framework for doing physics. So, this is the simplest definition that one can think of. Supposing you apply quantum mechanics into electricity and magnetism, then it becomes quantum electrodynamics. This became very famous after Richard Feynman, who worked extensively on quantum electrodynamics. If you apply quantum mechanics into optics, so you have this new branch of quantum optics. You apply quantum mechanics to gravity, so you have this bizarre world of quantum gravity opening up, which essentially leads into string theory, 11 dimensions, so on and so forth. So, in reality, quantum mechanics is the most fundamental theory that one can think of. It is the most fundamental theory that one can think of. So, it has successfully, I should say, replaced uh, classical mechanics. So, classical mechanics held sway right from the period of Newton until Einstein, Planck, and others rewrote the laws of classical mechanics and eventually replaced those laws with the laws of quantum physics. So it is the most fundamental theory that one can even conceive as of now. So what are its postulates? So what are the various postulates of quantum physics? To start with, it talks about dual nature of matter and light. Dual nature of matter and specifically radiation. Light, for a long period of time, was supposed to be made of waves, and the wave nature of the light became very apparent after the Young's double slit experiment. But Einstein had other ideas. When he discovered or described the photoelectric effect, he, you know, kind of described light to be made of indivisible packets of energy by name photons. And we have this very famous E equals h mu, the Einstein's frequency and energy relationship. H is the Planck's constant. And then other experiments like Compton effect, it added, you know, weightage to the fact that light radiation or light for that matter can exhibit particle nature. And experiments such as reflection, refraction, interference, diffraction, polarization, etc., once again reiterated the wave nature of light. So, what is light made of? Whether it is particle, whether it is a wave. So, it has been now by and large accepted that it behaves like particle, and there are occasions like where it behaves like waves. Similarly, inspired by all these research activities, French physicist de Broglie, Louis de Broglie, he proposed that if radiation, like in the form of light, can exhibit dual nature, then what about elementary particles like electrons, protons, neutrons, quarks, etc.? These elementary particles too exhibit wave-like behavior, and he described the wave nature of the elementary particles with the de Broglie's wavelength, which is h over p. So here h represents the Planck's constant. So Planck's constant is 6.6 into 10 to the power minus 34 joule second, and p is the linear momentum or the product of mass into velocity. So higher the wavelength, lower the momentum, etc. So this obviously should be the starting point of quantum physics. So there is always this dilemma: how do you start quantum mechanics? Where exactly do you begin quantum mechanics with? Well, it all starts with the dual nature of matter and radiation. Now, there is also a misconception about quantum mechanics, you know, which runs along these lines, suggesting that quantum mechanics is the physics of the small. Well, of course, it is very much relevant in the atomic world or atomic regime to speak of, but its relevance is not felt in the macroscopic world where we live. But that doesn't mean that quantum mechanics is not applicable. Quantum mechanics is applicable everywhere, from machines to molecules. Quantum mechanics can be applied, but it cannot be felt. For instance, if let's take an example. Like, for instance, if the mass of a ball, tennis ball, or any ball for that matter, is 46 grams, supposing it is traveling with velocity of 1000 meter per second, then the de Broglie wavelength associated will be equivalent to 10 to the power minus 34 meters. So such a small value, ridiculously small value. So the wave nature is not felt or apparent, and this is the problem. However, if you consider the mass of an electron, the mass of the electron is 9 into 10 power minus 31 kilograms. Supposing the electron is traveling with a velocity of 10 power 7 meter per second, then the de Broglie wavelength would be approximately, somewhere around 10 to the power minus 10, or I'm just giving you an approximate answer, 10 to the power minus 11 meter, which can be compared, roughly to the radius of the hydrogen atom. So quantum mechanics is very much relevant in the microscopic world, and it can explain the behavior of electrons, the behavior of all the subatomic particles to a large extent. Another startling proposal or postulate of quantum mechanics is the Heisenberg uncertainty principle. Heisenberg uncertainty principle. Proposed by Werner Heisenberg, this says that the product of uncertainty of the position and momentum of a quantum particle is always greater than or equal to h cross over 2. So this intrinsic uncertainty, I should say, is one of the features of quantum physics. This uncertainty in the measurement of, not even measurement, in the knowledge of position and momentum of particle, it has got nothing to do with the efficiency or the lack of it of any measuring instrument. It is an intrinsic uncertainty what we have to live with as far as the quantum world is concerned. Simultaneous measurement of momentum or position of a quantum mechanical particle is not possible. Supposing we represent the position of a particle with a wave, then based on this amplitude, you can say that, okay, somewhere down the line we can have, or we can have the location of the position of the particle. But what about its wavelength? And wavelength is indirectly related to momentum. So when you know the position, you don't have a lot of information about its momentum. On the other hand, if you have a long wave, something like this, you can tell a lot of information in terms of its wavelength. So wavelength is, inversely proportional to the wave number, and momentum is related to the wave number by this formula h cross k. So h cross is h over 2 pi, or in other words, it's called the reduced Planck's constant. So in this second wave, what we see here, we can easily tell what the wavelength would be, or we have a lot of knowledge as far as the momentum is concerned. But what about the position? The uncertainty connected with position is huge. So this is Heisenberg uncertainty principle for you. So the product of uncertainty. So you really need to measure both these parameters, which is simultaneous measurement is simply not possible. And this measurement has got nothing to do with the you know, technology or efficiency of the machines, what we operate. So these are some of the fundamental postulates of quantum mechanics. Another important postulate as far as quantum physics is, we need to use a lot of complex numbers. So complex numbers become very important in describing the waves or the matter waves. For instance, the matter wave psi of x comma t can be simply represented as a e power I kx minus omega t. And linearity is one of the important hallmarks of quantum physics, which is very surprising because classical mechanics is not linear. If you just leave the harmonic oscillator, all the classical systems, higher order classical systems, they have a lot of non-linearity associated with them. But quantum mechanics is surprisingly linear, especially the Schrodinger's equation. Schrodinger's equation is a perfect example of a linear equation. In the next few videos, we will analyze all these postulates in detail. So this is just a small introduction of what we have to expect, or what we have to expect in quantum mechanics. So see you next time. Take care.